solve some recurrence relations using recursive tree method. Let us take the first example. Tn equals 2t n by 2 plus n. Here we can see that the input size n is getting divided into two equal parts of n by 2, and during this division or merging n operations are involved. Since again it is a recursive call, the input size n by 2 is further divided into two equal parts of 1 by 2 into n by 2, 1 by 2 into n by 2, and so on. This n by 2 will also be divided in the similar manner, 1 by 2, n by 2. Here we can also see that the complexity of merging or division here would be n by 2. The input size is n by 2, and this equation is telling us that if the input size is n operations would be involved in that division or merging. Since this equation is telling us that if input size is n operations would be involved in division or merger. So here also we have seen, since the input size was n by 2, the number of operations involved in this division or merger would be n by 2. Same number of operations would be involved for this division also. The total number of operations for this level will also be n by 2 plus n by 2. Now at this level the input size for all nodes is n by 2 square. Now if we further divide it, that would be n by 2 cube, n by 2 cube for this, n by 2 cube for this node. It would be n by 2 cube for all these nodes. Since here the input size is n by 2 square, the number of operations involved at this level would be n by 2 square. For this also it is n by 2 square, n by 2 square for all the divisions at this level. N by 2 square for all the divisions at this level. If we compute the total number of operations at this level, they are also coming to be n. Now we have seen that at each level the total number of operations are n. If we generalize it, at kth level the number of input would be 2 to the power k. Here we can see that this division would stop when the value of n by 2 to the power k is equal to 1. And from here we can get the value of k equal to log n. So if we want to know the total number of operations involved in this process, those operations would be n plus n plus n till log n base 2 times. So the total number of operations are n log n. This is the maximum number of operations possible for this tree. Now Tn would definitely be less than or equal to n log n base 2, and from here we can conclude that Tn is big O of n log n. Let us solve another recurrence relation. Tn equal to 2t n by 2 plus 1. Here we can see from the recurrence relation that n is getting divided into two equal parts. So the input size is n. For this input size, the n is getting divided into two parts of size n by 2. And in each division or merger, we have one operation involved. Further at this level, we have n by 2 input size, which would further be divided as n by 2 square, n by 2 square at each node, like this. And at each division, one operation is involved. So one operation is involved here and one operation is here. And we can see that at this level, only one operation is involved, while at this level we have two operations. Now we can see at this level that input size is n by 2 square at each node. Now at the next recursive call, the input size will further partitioned as n by 2 cube, n by 2 cube at each node, and at each division or merger we have one operation involved. So total number of operations at this level will be 4. Here also the depth of the tree would be log n base 2, as we have seen in the previous example also. So the total number of operations would be 1 plus 2 plus 4 plus 8 plus and so on up to log n base 2 time. Here we can see that this is a GP with ratio equal to 2 with the first element equal to 1. So the sum of this GP is equal to a r to the power n minus 1 divided by r minus 1. It is equal to 1 r to the power n is the number of terms, that is log n base 2 minus 1 divided by r is 2 minus 1. The value of r is 2. Now from here we can see that 1 into 2 to the power log n base 2 is equal to n minus 1 divided by 1. So the maximum number of operations are n minus 1. We can also say that Tn is less than equal to n minus 1, or we can see that Tn is equal to big O of n. This is another recurrence relation where the input size is getting divided into n by 3 and 2n by 3, and at each level n operations are involved. So how we can solve it? Let us start with the input size n. So this n would be divided into n by 3 and 2n by 3, and in this division n number of operations are involved. And at this level the input size n by 3 is further divided into 1 by 3 of the input size, that is n by 3, and the second part would be 2 by 3 of n by 3, and here also it would be 1 by 3 of 2n by 3 and 2 by 3 of 2n by 3. This is how the input size is getting divided, and at each division n number of operations are involved. So here the value of n is n by 3, so total n by 3 input size would be involved. Here the input size is 2n by 3. So here if we compute the total number of operations at each level, it would be n for the level 1, and if we add these two, it will also be n. Here we can see that this tree is different from the previous examples, because here the input size is not getting divided into two equal parts, but it is divided into different sized parts. This particular side is very rapidly dividing because every time the input is getting 1/3 of the original size. And at this side the input size is decreasing very slowly because the input size is becoming 2/3 of the original size. The depth of the right side would be more than the depth of the left side. Here we can see that the input size is n by 3 to the power 0 at level 0, and n by 3 to the power 1, n by 3 to the power 2, and so on. So at the kth level the input size would be n divided by 3 to the power k. From here we can get the value of k equal to log n base 3. If we observe the right side, we can see that the input size is n divided by 3 by 2 to the power 0, and here the input size is n divided by 3 by 2 to the power 2, and so on. At kth level it would be n divided by 3 to the power 2 to the power k. Here we can see that left side of the tree would be having the least depth. So to compute the number of operations of left side, we have that it is n plus n till log n base 3 terms, it is equal to n log n base 3. This is the minimum number of operations in this recursive tree. Tn is greater than equal to n log n base 3, or we can say that Tn is big omega of n log n base 3. Okay, let us analyze the right side of the tree. So the input size is n divided by 3 by 2 to the power k at kth level. So from here we can get the value of k equal to log n base 3 by 2. If we analyze the right side, we can see that the value of k is equal to log n base 3 by 2. So the total number of operations of the right side would be n log n base 3 by 2. Since these are the maximum number of operations, we can say that Tn is always less than equal to n log n 3 by 2. And from here we can define the asymptotic notation as Tn equal to big O of n log n 3 by 2. So that's all for today. Thank you.